Hi everyone. So today we are jumping into Chapter 7. Now, Chapter seven's overall theme is powers and exponents, okay? And so we're going to be doing a lot of manipulating with different exponents and powers and things like that. Today's lesson is kind of a standalone lesson, all right, which makes it a good one to start with. It really doesn't necessarily relate to everything else we're doing in the chapter. There are some pieces of it that I guess that do. But what we're looking at today are what's called power functions. And power functions are any functions in the form y equals x to the n. So let me just write that part bigger because that's pretty important. Y equals x to the power of n. So we've already talked about, like, for example, y equals x squared. That's one of these power functions. But now we're also going to include x cubed, x to the fourth, x to the fifth. Basically, we can put whatever power we want in there for n. Okay? And we kind of divide these into two categories because they have some different characteristics. So we have even power functions and odd power functions. And when I'm referring to even and odd, I'm referring to the value of n. Okay, so like even power functions would be like x squared, x to the fourth, x to the sixth, etc. Well, I guess I should do one of those. Odd power functions would obviously be like x cubed, x to the fifth, and so on. Okay, so what I want us thinking about is what the graphs of these things look like versus the graphs of these things. Okay. And what I'm going to do here, I'm going to try to get fancy. Let's see if this works. Nope, wrong one. That's what I wanted. I'm going to head over to Desmos, which is an online graphing calculator. And I'm going to graph some of these because normally in class right now, I would be asking you guys to graph these on your calculator and tell me what they look like. But we already know what x squared looks like. So this red one here is x squared. All right, what about x to the fourth? Okay. Or x to the sixth. Okay, let's get crazy and do x to the power of 20. All right, that's that orange one that popped up. So you can see all the colors over here. I don't think I can make that smaller, but I can zoom this in. All right, so overall, what you should notice is these all have the same general shape. Okay, x squared, of course, is our parabola that we know and love. But they all of these are shaped sort of like a parabola. Notice they get a little flatter down at the bottom, and we're going to talk later about why that happens. Okay, they do get a little flatter as the numbers get bigger, and then they also get a little narrower up here. But overall, they always have like a U shape to them. Okay, they also always contain the point 0, 0, and they're always symmetric over the y-axis. Like I could always fold them in half right along this line here, and they would line up with one another, okay? So we're going to write some of those things down that we just kind of observed by looking at the shapes of those graphs. That even-powered functions are always U-shaped, okay? And I'm going to put like a parabola. Now, chances are, as we go through this lesson, you guys are going to just start referring to these as parabolas. I should point out to you that technically only x squared gets to be called a parabola. But you're right, that the rest of them are all shaped similar to a parabola. Okay? They always contain the point 0, 0 until I throw some other numbers in there. But then they're not considered to be power functions anymore. So if it's just a single, like x to some power, always going to be right at 0, 0. Okay? And always symmetric over the y-axis. And that comes from the fact that when you square a negative number, it comes out to be the same as if you had squared the positive number. So for example, like -2 squared is equal to +2 squared. And I could do that with any of the even powers. So -2 to the sixth is also equal to +2 to the sixth. That's where that symmetry comes from. Okay? So that's what you need to know about even power functions. Now let's take a look at what happens with odd power functions. So I'm going to basically just switch this and make this a power of 3. Okay, actually I'll get rid of these for a second. So you can see x to the power of 3 looks very different than x squared did. I zoom in one more. There we go. Okay, so this one looks very different than x squared did. But when you actually dig into it, it's not all that different. What it really is this side, this right side of the graph here is just like a parabola. If I graphed x squared along with that, okay, and it's not going to be exactly the same because it's a different power, but you can see that these have kind of the same general sloping shape, okay, that this half of the red one looks just like half of a parabola. Okay, get rid of that guy. This half, though, instead of going up this way, like a parabola would, it heads downward, okay? So it's almost like I just took the one half of a parabola and flipped it over. And that comes from the fact that when you raise a negative number to an odd power, it stays negative instead of turning positive like in the parabolas, okay? And then you'll notice that like x to the 5th, x to the 7th, all of them have, again, that same general shape, all right? They have sort of that up and over and up type shape, okay? And they're all related to those even power functions, except the left side of the graph is heading downward instead of heading upward, okay? And again, they get a little bit flatter around the middle as your power gets higher, and we'll talk about that, later on with this lesson, okay? So for my odd power functions, you should know, I'm just going to draw a line here so you know this is all odd. These ones are sort of shaped, okay? I wish I had a good word for that. I really don't. I usually refer to that as like the squiggle shape, okay? But they kind of go up and over and up again. These ones also contain 0, 0, so that's actually a similarity between the two. Okay? These ones are not symmetric over the y-axis. I can't fold these ones in half. But these ones have what's called reflection symmetry. I'm sorry, not reflection. Wrote the wrong word there. Rotation symmetry. Okay? Rotation symmetry around the origin. And I'll show you what that means in just a minute. Okay, so looking back at my graphs here from a second ago, let me just get rid of these other guys and look at just one of them. Okay, x cubed. If I put my finger right here in the center of the graph, okay, and took this graph and spun it, it would land back on itself. And I can't demonstrate so much how to spin it when you're just looking at a screen. But if I took this and then I took this guy and spun it down this way, this half of the graph would land on top of this half of the graph. So there would be a rotation there. Okay, so that's what I mean when I say it has rotational symmetry. It doesn't have reflection symmetry, but it has rotational symmetry. Okay? So then the question is, what happens if I throw a negative in here? So like, for example, what I mean by that is, what if I make it negative x squared? Now, let's be careful here for a second. This is not saying that I'm plugging in a negative value for x. This is like putting a -1 out in front of the x squared. Okay, so it's not saying I'm making the x value negative. It's saying I'm sticking a negative sign out in front of the x. Okay, we've talked about this actually a ton already. We probably already know the answer to this, but let's go take a look, shall we? There it is. I'm going to go back to, let's go x to the 4th, just so we're not always looking at x squared. Here's x to the 4th. If I throw a negative in front of x to the 4th, watch what happens. Boom. It flips over. Okay? That shouldn't be too earth-shattering because we've done that with parabolas already. In fact, we've done that with a lot of different graphs. Back in Chapter 2, when we did all the parent functions, we talked about how negative signs flip things over. Okay? If I took x to the power of 3 and then did a negative version of that, so negative x to the power of 3, notice what they do is they flip as well. This red line really flipped down here, okay? And this red line down here flipped up here, okay? So that negative sign is just making everything sign reverse, okay? So ultimately what you need to know here is the negative sign makes the graph flip upside down. Whoops, flip upside down. So it's going to point in the opposite direction. Okay, we are actually skipping example 1 because example 1 doesn't really make sense with this lesson, I don't think. Okay, personal opinion here. But so get rid of example 1 there, but example 2 is where things get important. I might actually try to leave this part of the notes out here. Maybe not. Okay, so looking at example 2, it says the point -2, 256 is on the graph of a power function. Is the power function even or odd? Okay, so look at what's going on here. You have an x value that was negative and it turned positive, okay, when I raised it to a power. So what this is really saying is I'm doing -2 to some power and it turned into a positive 256. And I want to know what kind of number does that n have to be, okay? Well, it must be an even number, because that's when your negatives all cancel out and it turns back to positive, is when you have an even number of negatives. Okay, so I'm just going to make a note here that my negative turned positive. Okay, now if I had had the point, let's just say I'm making up something different here. If I had had the point -3, -27, let's say, then I would say, well, that must be an odd power because I plugged in a negative number and got a negative number back. Only odd powers can do that. Even powers turn everything back to positive. Okay, think about squaring things. Okay? Then it says write an equation for the power function. Well, the equation is going to be really simple. We know it's going to look like this. And the only thing we really need to worry about is what is this power right here? Now, the good news is we already know that it's even. Okay? I just need to know what power turns a -2 into a 256. And I generally think that the easiest way to do this is quite honestly just guess and check. Okay? So I'm going to take -2, and of course I'm going to remember that when I'm doing negatives up to powers, I need it in parentheses. I even wrote it in parentheses here. So I want to raise -2 to some power and have it come out to be 256. And again, something that will help with the guessing is we do know that it's an even number, right? So maybe -2 to the 4th. Nope, that's not 256. -2 to the 6th. That's not 256. -2 to the 8th. By the way, some of you probably already knew the answers to some of these ones, so you wouldn't have had to guess them. Okay, I'm kind of making a point here. -2 to the 8th. Oh, hey, look at that. -2 to the 8th is 256. Okay, so that means 8 is my magic exponent, and that means my equation must be y equals x to the 8th power. That's all there really is to that. Okay? Then it says name 3 other points on this graph. I want to give you 2 easy answers to this question. Okay? Not that the other answers aren't easy, but I want you to look back at this for a second. I don't care whether this is an even power function or an odd power function. Both types of function are always going to contain 0, 0. Because if you think about it, 0 to any power is going to equal 0. Okay? So any power function, even, odd, whatever, no matter what that exponent is, 0, 0 is going to be there. Okay? And then another easy one to plug in, if you take 1 and plug it in for x, 1 to any power is just going to be 1. Okay? So these 2 points right here show up on every power function. Okay? Actually, let me make a quick point about that. Back to my graphs. Get rid of my -1 here. Okay, so I've got x cubed there. Let's maybe throw an x to the 4th in there. Maybe an x to the 6th. And let's get crazy with an x to the 11th. Okay, so I've got 2 evens, 2 odds in there. My graph looks all kinds of crazy. But if I zoom in here, all right, so I'm zoomed in really, really close, notice that all of these graphs share 0, 0. Okay, all of them go through 0, 0. They also all go through 1, 1. Okay, so 0, 0, and 1, 1. Those are nice, safe bets for every single power function. They're always going to contain those 2 points. And again, that's because 0 to any power is 0, and 1 to any power is 1. Okay? So now we need one more point, okay? And this can be anything you want. Just pick an x value. I don't know, maybe 3. Okay, pick an x value. And then we really just want to do 3 to the 8th power, okay? So in your calculator, 3 to the 8th power. It could be any number to the 8th power. I get 65, 61. So my coordinate would be this, okay? And again, just to make sure you understand where that came from. I chose 3. I just picked this number. Random pick. Okay? And then here I just did 3 to the 8th power to get 65, 61. Okay? And that's all there is to a problem like that. Okay? Okay. One more thing I just realized that I never did because we did the graphs on Desmos. Under each of these, I would maybe just sketch this. What does this look like? Looks like this. Okay? We know that it has 0, 0. We know that it has 1, 1. Every single one of these is going to have that same general shape and those same 2 points. Odd power functions are going to look like this. Should have put arrows on these. Also containing 0, 0. Also containing 1, 1. Okay? Okay, so homework for tonight is going to be Lesson Master 7-1B, and since that's sort of a departure from what I was originally planning for today, it is separate from your homework packet. It's just a separate sheet, and then I'll just collect it from you tomorrow. So we'll get those handed out to you, and you can get started.